Hello students, myself Dilip Udani, Assistant Professor at LG Institute of Engineering and Technology. The name of the unit is Ordinary Differential Equation of Higher Order, and today's topic is Legendre's Linear Equation. So let's start. First of all, I will make you understand what is Legendre's linear equation. A differential equation of the form a0 ax plus b the whole raised to n, nth derivative of y with respect to x plus a1 ax plus b the whole raised to n minus 1, n minus 1 derivative of y with respect to x plus a2 ax plus b the whole raised to n minus 2, n minus 2 derivative of y with respect to x plus dash 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 plus a n y equals to q of x is called Legendre's equation. Legendre's linear equation. To solve this differential equation, let ax plus b equals to e raised to z. Now, differentiating this equation with respect to x, so a will be as it is, derivative of x is 1, b is a constant value, its derivative is 0, derivative of e raised to z is e raised to z, and z is a function of x, so we have dz by dx. So from here we will find out dz by dx. So dz by dx, that is equals to a upon e raised to z, and a will be as it is, and e raised to z, that is ax plus b. So this is equation number 1. If in this equation, if you replace ax plus b by e raised to z, the given differential equation will become f of dy equals to function of z. Now we will find out dy by dx, that is equals to dy by dz into dz by dx. So this is equals to dy by dz, replacing dz by dx by a upon ax plus b. Now multiplying this equation by ax plus b, so we have ax plus b dy by dx, that is equals to a dy by dz, and this is equals to a dy, where d, that is equals to d by dz. Now similarly we will be having ax plus b the whole square, d square y by dx square, that is equals to a square d minus 1 y and similarly ax plus b the whole cube d cube y by dx cube, that is equals to a cube d minus 1 d minus 2y, where this one d equals to d by dz. Now if you replace ax plus b dy by dx by a dy, ax plus b the whole square d square y by dx square by a square d minus 1y, and finally ax plus b the whole cube d cube y by dx cube, that is equals to a cube d minus 1 d minus 2y in the equation 1, and after simplification you will get function of dy equals to rz. Now this is a linear differential equation with constant coefficient. Now you can solve this differential equation with the methods discussed with you. Now I will make you understand this concept with the help of example. Example number 1, solve x plus 2 the whole square d square y by dx square minus x plus 2 dy by dx plus y equals to 3x plus 4. Here the given differential equation is Legendre's linear differential equation. As with dy by dx we have x plus 2 the whole raised to 1. With d square y by dx square we have x plus 2 the whole square. Now to solve this differential equation, let x plus 2 equals to e raised to z. Therefore x equals to e raised to z minus 2. Now if we will take logarithm both sides, we have z equals to logarithm of x plus 2, and in the given differential equation we will replace x plus 2 dy by dx by, see here the coefficient of x is 1, so we will write down 1 dy, where this one d is d by dz. Similarly we will replace x plus 2 the whole square d square y by dx square by 1 square d minus 1 y, where d equals to d by dz. Now in the given differential equation, that is x plus 2 the whole square d square y by dx square minus x plus 2 dy by dx plus y equals to 3x plus 4. We will replace x plus 2 dy by dx by dy, x plus 2 the whole square d square y by dx square by d minus 1y, and x by e raised to z minus 2. Therefore d minus 1y minus dy plus y equals to 3, replacing x by e raised to z minus 2 plus 4. Now we will simplify this equation taking y common and multiplying d minus 1 by d. So we have d square minus d plus 1 y equals to multiplying e raised to z minus 2 by 3. So we have 3 e raised to z minus 3 to the 6 plus 4. So we have d square minus 1d, that is minus 2d plus 1 y equals to 3 times e raised to z minus 6 plus 4, that is minus 2. Now this differential equation is of the form function of dy equals to rz, as this is function of z. Now its solution is y equals to cf plus pi. Now first of all we will find out cf, that is complementary function. To find cf, we will write down f of d equals to 0. Now in f of d equals to 0, we will replace d by m. So we have f of m equals to 0. Here f of d is d square minus 2d plus 1. So in this function of d, we will replace d by m. So we have m square minus 2m plus 1, that is equals to 0. Now we will split the middle term 2m to factorize this equation. We will find two numbers whose product is 1 and addition is 2, and those two numbers are 1 1 ja 1. M square will be as it is. Now splitting minus 2m as minus 1m, minus 1m plus 1 will be as it is. Now taking m common, so into bracket we have m minus 1. Now taking minus 1 common, so into bracket we have m minus 1, that is equals to 0. Now taking m minus 1 common, so into another bracket we have m minus 1, that is equals to 0. Equating m minus 1 to 0, we have m equals to 1 or m equals to 1. So based on these two repeated values of m equals to 1, we will write down CF, that is C1 e raised to 1z plus C2 z, as this one is repeated, e raised to 1z. This is equals to C1. We have taken x plus 2 equals to e raised to z. So replacing e raised to z by x plus 2 plus C2. X plus 2 equals to e raised to z. So z equals to logarithm of x plus 2 and e raised to z is x plus 2. Now we will take x plus 2 common from these two terms. So this is equals to x plus 2 common, C1 plus C2 logarithm of x plus 2. So this is required CF. Now we will find out Pi. Pi equals to 1 upon f of d rz. 1 upon f of d is d square minus 2d plus 1 and rz is 3 e raised to z minus 2. Now we will apply this operator on 3 e raised to z as well as on this constant value. So this is equals to 1 upon d square minus 2d plus 1, 3 e raised to 1z minus 2 is a constant value, 1 upon d square minus 2d plus 1, and here we will write down e raised to 0z. Now if you replace d by 1, you will get 0 in the denominator. So what we will do, we will multiply the result by z and we will differentiate the denominator. Derivative of d square is 2d minus 2 same, derivative of d is 1 and this one is constant, so its derivative is 0. We will keep 3 e raised to 1z as it is. Then after minus, now replacing d by 0, d square will become 0, minus 2d will become 0, and we have 1 in the denominator only, so this is minus 2 by 1, that is minus 2, and if you multiply 1 by 2 you will get 2. Now here if you replace d by 1 you will get 0 in the denominator. So again we will differentiate 2d minus 2 with respect to d. So derivative of 2d is 2 and this 2 is a constant value, so its derivative will become 0, and we will multiply the result by z. So it will become z square into 3 by 2 into e raised to z. So this is equals to 3 by 2 z square e raised to 1z minus 2. Now 3 by 2 will be as it is. Now we will replace z by logarithm of x plus 2 the whole square and e raised to z, that is x plus 2, and this minus 2 will be as it is. So this is the required pi. At last we will write down the general solution y, that is equals to cf plus ti. Cf is x plus 2 into bracket c1 plus c2 logarithm of x plus 2 plus pi is this one, that is 3 by 2 logarithm of x plus 2 the whole square x plus 2 minus 2. So this is the required general solution of the given differential equation. Now we will see example number 2, that is solve the given differential equation. Now you can see that with single derivative in multiplication we have x plus 1, and with a double derivative in multiplication we have x plus 1 the whole square. So this is Legendre's linear differential equation. Now to solve this differential equation, let x plus 1, that is equals to e raised to z. Therefore taking logarithm both sides, we have z equals to logarithm of x plus 1, and from here we will find out x. Therefore x equals to e raised to z minus 1. Now in the given differential equation, that is x plus 1 the whole square d square plus x plus 1 d plus 1 y equals to 4 cos ln x plus 1. We will replace x plus 1 d by 1 d and x plus 1 the whole square d square by 1 square d minus 1. So this is equals to 1 square d minus 1. We have replaced x plus 1 the whole square d square by 1 square d minus 1 plus, now replacing x plus 1 d by 1 d plus 1 y, that is equals to 4 cos of ln x plus 1, that is z. So replacing ln x plus 1 by z, where this one d is d by dz. Now we will simplify this equation. D into d, that is d square, minus d into 1, that is d, then after plus 1d plus 1 y equals to 4 cos z. Now minus d plus d will cancel out. We have d square plus 1y equals to 4 cos z. So this is equals to d square plus 1y equals to 4 cos z. Now this differential equation is of the form function of dy equals to rz, and its solution is given by y equals to cf plus pi. So first of all we will find out cf. To find cf we will write down f of d equals to 0. We will replace d by m. So we have f of m equals to 0. Here f of d is d square plus 1. So in f of d we will replace d by m. So we have m square plus 1 equals to 0. Therefore we have m square equals to minus 1, and minus 1, that is nothing but I square. So we have m equals to plus minus 1i. 1 is the imaginary part and 0 is the real part. Now based on this complex number we will write down CF. So CF, that is equals to C1 e raised to 0z, but e raised to 0z, that is 1, so no need to write down e raised to 0z. Cosine of 1z plus C2 e raised to 0z is 1, sine of 1z. So this is equals to C1 cosine of, replacing z by ln x plus 1 plus C2 sine, replacing z by ln x plus 1. Now we will find out pi. Pi, that is equals to 1 upon f of d rz. So pi, that is equals to 1 upon f of d is d square plus 1 and rz is 4 cosine of z. Now think about case number 2. Here the value of a is 1, so we will replace d square by minus 1. And if you will replace d square by minus 1, you will get 0 in the denominator. So what we will do, we will multiply the result by z. We will differentiate the denominator. 1 upon derivative of d square, that is 2d. 1 is a constant value, so its derivative is 0. 4 will be as it is. Cosine of z will be as it is. Now 4 by 2, that is 2. So 2z will be as it is. And 1 upon d cos z. D means derivative and 1 upon d means integration. And integration of cos z, that is sin z. So this is equals to 2. Now we will replace z by ln x plus 1 sin, replacing z by ln x plus 1. Now the general solution is y equals to CF plus PI. CF is C1 cos of ln x plus 1 plus C2 sine of ln x plus 1 plus Pi is 2 ln x plus 1 into sine of ln x plus 1. So this is the required general solution of the given differential equation. So in today's lecture we have seen Legender's linear equation. We have seen the standard form of Legender's linear equation. We have discussed how to find out the solution of Legender's linear equation. And we have gone through 2 examples based on this topic. Thank you for watching this video.